Suppose that phi is a homomorphism from U15 to itself, and the kernel consists of the elements 1 and 11. By the way, remember kernels are subgroups. So that should be a subgroup if this is going to be a valid kind of problem. And you can double check in your mind here, do calculation in your head. 11 has order 2, 11 squared is 121. 121 mod 15 is 1 because 15 does divide evenly into 120, right? Double check that, yeah. You're told phi of 7 is 8. Find all the elements of U15 that map to 8. This seems like, I think, a hard problem. Like, what in the world? How in the world can you possibly do this? This problem is based on knowing a fundamental fact about homomorphisms. It's in Theorem 10.11 or 10.1, excuse me. It's property 6. I don't know if you found that or not in looking through the book or through your notes. It's a pretty important property, actually. If phi of g equals g prime, then this is called the preimage of g prime. Remember, homomorphisms don't have to be one-to-one. So the inverse function of phi need not exist. But this notation is still used. It's called the preimage. We've talked about that before. It's everything in G that gets mapped to G prime. And this theorem says it equals this coset of the kernel. And that's relevant for this problem, because in this problem, phi of 7 equals 8, we're trying to really find, well, if we're trying to find everything that maps to 8, so we're trying to find the preimage of 8 by the theorem 10.1 part 6, the preimage of not 7 but 8. This is not a one element. This is more than one element. This is a set. According to this theorem, it's the coset 7 cur phi in the theorem. So phi of 7 equals 8. The 7 is playing the role of the G, and the 8 is playing the role of the G prime. That's supposed to be a G there. The 7 is playing the role of the G, and the 8 is playing the role of the G prime. The preimage of 8, everything that is in the domain, which, by the way, the domain and codomain are both the same here. They're both U15. Everything in the domain that gets mapped to 8 is this coset. Since you're told the kernel is 1, 11, you have to compute this coset. 7 times 1 is 7. 7 times 11 is 77, but mod by 15, what would that be? 2? Right? 77 mod 15 would be 2. There's the answer. 7 and 2 are the elements that map to 8. Okay. Notice this is not a subgroup. Doesn't contain 1 for one thing. It's not a subgroup of U15. Cosets in general are not subgroups. They're only subgroups when they equal the original subgroup. AH equals H if and only if A is in H. So the coset is only going to be equal to H and only going to be a subgroup, in fact, if the representative is already in H. Otherwise, it's not going to be a subgroup. Okay. So that's knowing a fact, a pretty important fact in that theorem that I do talk about in the lectures. Skip 15, let's move on to 16. 16 also seems like it might be hard, and I think it is unless you really take the hint to heart. Suppose phi is an element of the automorphism group of Z9. So now we're talking automorphisms, isomorphisms from a group to itself. These are not just one operation preserving, but also one-to-one and onto. Suppose phi of 4 is 2, find phi of 7. Okay, so the hint says 4 is a generator of Z9 and phi is operation preserving. So, and remember the group operations addition here. We want to find phi of 7. I hope you realize it's useful to try to write 7 as a bunch of 4s added together. 4 is a generator. So some number of 4s added together should give you 7 mod 9. 4 plus 4 does not. 4 plus 4 plus 4 is 12. Mod 9 is 3, does not. 4 4s gives you 16. Mod 9 is 7. There we go. 7 is 4 added to itself 4 times. Do you need to put the mod 9 in there? No, you don't have to put it in there. It's understood. You're working in this problem. So we are working in Z9. I will go ahead and give that as a reason in Z9. And here's where you use its operation preserving. And the operation is addition, so we continue to use plus signs. We're assuming phi of 4 is 2, so we get 2 plus 2 plus 2 plus 2. Mod 9 is still 8. The answer is 8. Phi of 7 must be 8. And theoretically, you could find phi of every input in Z9 here, and they should all be unique because we're assuming it's on an automorphism 1-to-1. Will that really happen? I suppose we should maybe double check and see if it happens. If it didn't happen, maybe it's not valid for an automorphism of Z9 to map 4 to 2. Maybe that's not valid. No, we'll have to look. You'd have to experiment with that and see if that happens. I'm kind of assuming it's valid. 17. Let G be a group with order 125. Prove G must have an element of order 5. Doesn't sound easy again. What's the best overall strategy here, you think? Did you think strategy? I mean, one big theorem is very relevant. What theorem? Real fundamental is very relevant. Person's name starts with an L. Lagrange, right? Lagrange's theorem is relevant. So G has order 125, which is 5 cubed. Elements of G, and not just subgroups of G, but also elements of G have to have orders that divide 125. Only possibilities are 1, 5, 25, and 125. Lagrange implies the possible orders of subgroups, but also elements are 1, 5, 25, 125. Of course, the identity element is going to be the only one of order 1. So strategy here, what do you think? Cases? Maybe not fun to do cases, but you know, or maybe you could think contradiction, perhaps, would be another thing you could think about, maybe within the cases. You could maybe start by assuming G is cyclic. You know, what if G is cyclic as one case, and what if G is not cyclic as another case? I'm not going to write out the proof in sentences for sake of time, but we're just sort of writing down ideas. The case 1, G is cyclic. So that means G is generated by something where that element has order 125, right? Well, actually, you wouldn't even need to mention that, actually. What am I thinking of when I'm saying you wouldn't even need to necessarily even mention the A? Thinking of another very important theorem from earlier in the book. something very fundamental about cyclic groups. The fundamental theorem of cyclic groups would basically mean we're done, because G being cyclic would mean the fundamental theorem of cyclic groups says cyclic groups have unique subgroups of each order that divides the original group, including subgroup of order 5. And any subgroup of order 5 has got to be cyclic. It's got to have a generator that's got to have an element of order 5. So you wouldn't even need to say this. You could. If A has order 125, what power of A would have order 5? A to the 25th power. Done. There's an element of order 5. Actually, you could say what all the elements of order 5 are here as well. If you wanted to, it's not necessary, but this is worth remarking. Also, A to the 50th would have order 5. A to the 75 would have order 5. A to the 100 would have order 5. Oops, not 1,000. These all have order 5. There are 4 elements of order 5 generating the unique subgroup of order 5. So the case 2 would be, what if G is not cyclic? G is not cyclic, so G does not have a generator, so there are no elements of order 125. That means all elements, non-identity elements, have either order 5 or 25. If one has order 5, we're done. But what if one has order 25? Or what if they all have order 25? Or is that even possible? If you assume to the contrary that every non-identity element has order 25, what's the contradiction? If all non-identity elements have order 5 or order 25, is that possible? Not possible. Why? This is probably maybe not the best way to, this is probably not the best way to phrase it. Then we have a contradiction right away. Because why? Because if A has order 25, A to the 5th would have order 5, right? Done. Contradiction. They can't all have order 25. That's probably kind of awkward way to say it, but that's the essence of what's going on. Okay, so it's got to have at least one element of order 5. Actually, it's going to have more than one. What if I change the problem to being, let G be a group of order 125? I mean, let's make it a question. Must G have an element of order 25 or not? 25, not 5. Let G be a group of order 125. Is it necessary for G to have an element of order 25? It's a question. Give reasons to your answer. Hint. Think extra. Go ahead. Uh-huh.
Why is A to the 5th the order of A to the 5th?
Because if A has order 25, then A to the 5th squared is going to be A to the 10th, which is not E. A to the 5th cubed will be A to the 15th, which is not E. A to the 5th to the 4th will be A to the 20th, which is not E, but A to the 5th to the 5th will be E. And that'll be the lowest power of E, A to the 5th. That'll get you back to the identity. There's a theorem in chapter 4 that makes this computation mechanical, something you could, a formula, but knowing this kind of thing, I wouldn't expect you to necessarily have to give reasons for this. Okay. There's the reason. Must G have an element of order 25? Think external direct products. What's one way to generate an abelian group of order 125 with no elements of order 25? So the answer is no, it must not. It does not necessarily have to have an element of order 25. I'll get you started here. You finish it for me? Yeah, a bunch of Z5s. 3 of them to have order 125. This group is order 125, but no elements of order 25 or 125. All the 9 identity elements have order 5. The LCM fact with regard to external direct products could be used to prove that. Number 18, let G be a group of order P squared where P is prime. Prove the center of G cannot have order P. I hope this was the easiest one perhaps for you. Perhaps if you got this far and were up on remembering your theorems. What theorem's relevant here? A couple of them actually.
The corollary from theorem 9.8.
Corollary theorem 9.8. Yep, that's certainly something that could be used. If G is a group of order P squared where P is prime, then G is abelian, so the center must be all of G, so I can't have order P. That's certainly the most direct proof. Can you just quote corollaries like that? Yeah, you can. You could say we have a corollary that says this. If you want to say not allow yourself to quote corollaries, the GZ theorem is relevant. Let G be a group and let Z of G be the center of G. If the quotient, the factor group G mod the center is cyclic, then G is abelian. This is kind of a strange theorem actually, because you can conclude more. It says if the factor group is cyclic, then G is abelian, but that would also imply the center is all of G, which would imply this factor group is trivial. If factor group is cyclic, it must be trivial, just one element. Weird. That's kind of weird. The author does emphasize it's really the contrapositive of this that's more useful, you might say. If G is non-abelian, then the factor group can't be cyclic, which is, again, it's kind of a strange fact, and so strange facts are often useful. Anyway, that's something that can be used here, along with Lagrange's theorem. Could use an argument by contradiction. Suppose to the contrary, that the center has order P. Then the factor group of G by the center of G by Lagrange's theorem has order of G divided by the order of the center, which will be P squared divided by P, which is P, where P is prime. And we know also by Lagrange's theorem that groups of prime order are cyclic. Therefore, the center is cyclic. Therefore, by the GZ theorem, G must be abelian, which would imply, just like I said a minute ago, the center is all of G, it's order P squared. the GZ theorem. Therefore, the center equals all of G, so the center has order P squared, but that's a contradiction because we assume the center had order P. So there's a little longer proof. Contradiction. There's a little longer proof using the GZ theorem and Lagrange's theorem. Certainly that corollary is much shorter proof. First isomorphism theorem. Talked about this last Friday. Let's actually do some of the details here. So we've got a group homomorphism from G to G bar. This mapping psi defined by this equation is an isomorphism. Not from G to G bar, but from G to the image of this homomorphism. Prove this fact in steps. Step 1, show psi is well defined. We've done lots of well-defined stuff. I think a well-defined proof needs to go on the exam. I'm not sure if it'd be this one. Maybe there's another one. What other ones do we do? We talked about the orbit stabilizer theorem, well-defined one. We talked about the coset multiplication, well-defined one. There are other ones in the reading as well, showing functions are well-defined. The issue is, again, suppose you've got two different representatives of the same coset. G1 and G2. So I'm supposing this is true. And what do you have to show? You have to show that phi of G1 equals phi of G2. You also have to know, to do that, you have to know deep in your soul properties of cosets. Remember the lemma, the big long lemma, kind of like analogous to the invertible matrix theorem in linear algebra. There's so many parts to it. You want to get those properties in your mind deeply embedded. AH equal BH if and only if A inverse B was in H. So these are cosets. G1 curve phi equals G2 curve phi. That's actually an if and only if. I'll go ahead and put a backwards arrow as well. G1 inverse G2 is in the kernel. You could also say G2 inverse G1 is in the kernel. The roles of G1 and G2 are symmetric. But the inverse does, excuse me, the inverse does need to be put on the element on the left, not the one on the right. Why? I'll let you study it to remind yourself why. We did talk about that. But what does that mean? That's equivalent. I'm doing double arrows for a reason here. That's equivalent to saying phi of G1 inverse G2 is the identity. In G bar, call it E bar. But by the fact that phi is a homomorphism, so it's operation preserving, that's equivalent to this. I did essentially two steps there at once. That's okay here. I think we've done that enough that we could call that okay. And now just multiply both sides on the left by phi of G1. And for extra emphasis, we could say this is equivalent to psi of G2 curve phi equaling psi of G1 curve phi. Okay, the proof for step 2 is the exact same set of equivalencies, but in the opposite logical order. Because what does 1-to-1 mean? If the outputs are the same, the inputs must be the same. So with 1-to-1, start by assuming this is true, that the outputs of psi at these two inputs are the same. Why must those inputs be the same? Go backwards. These being the same by definition of psi means these are the same, which by multiplication by phi of G1 inverse on the left on both sides gives this, which by the fact that phi is a homomorphism gives this, which means that element that you plugged into phi is in the kernel, which means by properties of cosets that these two cosets are the same. So if, as I did last year, this were on the exam, I'd be a little bit more lenient here about sentences. You could say, maybe we don't want to have this suppose, we could say, the following set of equivalencies proves both step 1 and step 2. Though, should give reasons. And properties of cosets. Definition of kernel, etc. Okay, step 3, show psi is onto the image phi of G. Give me an arbitrary element of the image phi of G. Call it G bar. That implies there exists a little g in G such that phi of G equals G bar. And by the formula for psi, you're done. The left coset G curve phi will be something like it's mapped to G bar. Step 4, operation preserving. Suppose, or you want to consider this expression, psi of this product. These are the cosets, left cosets, they're in the factor group. How do you multiply them? By multiplying the representatives. Then use the formula for psi. That's phi of G1 times G2. Then use the fact that phi is operation preserving. Right? That's got to be relevant. We're done. Again, reasons should be given. Coset multiplication there, definition. For the formula for psi itself. Phi is assumed to be a homomorphism, it's operation preserving, and the definition of psi again. Got a few minutes left. Let me just remark in those few minutes that you should also be able to prove properties of homomorphisms, both the properties in theorem 10.1n and 10.2. Should be able to prove these. And in particular, especially 4, 5, and 6. Or use a subgroup test. Actually, I'm not sure why it's not mentioned here. You could say more. In fact, we did this last week, I think. Last Friday, or was it? Must have been last Friday. We proved that the kernel was a normal subgroup. I don't know why the author didn't bother mentioning that as part of the theorem. not just a subgroup of G, it's always a normal subgroup of G. That's why we can form the factor group for the first isomorphism theorem. No matter what the situation is. The kernel, no matter what G, the group G is, the kernel is a normal subgroup. Maybe you want to put the word normal in there in your book if you want to go ahead and write in your book there. Property 5 should be able to do. It's properties of cosets and the meaning of kernel. Property 6, the one we used at the first problem there today, should be able to prove that too. If you look at the book's proof, they use property 5. So probably if I put property 6 on the exam, I would say what property 5 is, and would say you can use this property. And the properties in theorem 10.2. This is properties of homomorphisms again, not isomorphisms. I mean, isomorphisms are homomorphisms, so these are also properties of isomorphisms. But homomorphisms don't have to be one-to-one or onto, so all these can be proved without assuming one-to-one or onto, just using operation preserving. And the ones that stand out to me as things that are problems I like to give are 8 and 9. 10 is interesting as well. 10 is saying if phi is onto and the kernel is trivial, then in fact phi must be an isomorphism. In fact, that means the kernel being trivial implies the function must be one-to-one. That's what's left to show here in number 10 is that phi is one-to-one. By the way, these properties do come up in linear algebra in various forms. These things I'm talking about with regard to linear transformations, though with different notation and different terminology. So a lot in the reading. I hope you have done the reading. It might feel overwhelming. So many examples, so many theorems. I tried to highlight what I thought was most important in the lectures. So as far as distilling what I thought was most important, the lectures are helpful, the homework's helpful, the sample exams are helpful. Sometimes, we don't have enough time to either do something in the lecture or in class here. And so exercises, problem solving still is relevant to go beyond. All right. See you at 7:20 on Wednesday.